And here it is, sp3 hybridization. So here we are in the type of hybridization where we're going to combine an s orbital with three p orbitals to make a tetrahedral shape. Okay, it's called a tetrahedron, but we'll call it a tetrahedral as well. And I call it the tetrahedral family, meaning if we have sp3 hybridization, the electron domain geometry of where the electrons exist, okay, will be in a tetrahedral shape. And the reasoning behind that is because these four equal orbitals now, which are a blend of these three orbitals, will repel themselves to find this stable shape. And each of these shapes, or each of these, I should say, orbitals, okay, these what we say sp3 orbitals will have 109.5 degree bond angles. That is the stability at which four pairs of electrons. If I when I blow up four balloons, they will also do that. I like to think of this tetrahedral family is we have this planar. We started this with sp2. We had trigonal planar where we had basically, and that's not drawn very well, basically a triangle where it's probably better this way, where the orbitals, the sp2 orbitals, repel themselves. So these electron wave functions, probability functions, where electrons exist, would repel themselves into this 120 degree bond angle. By adding one more orbital or hybridized orbital, what would happen is we would get this shape. Now, if you think carefully with me, if you think that these three are supposed to be pointing down, so think of a planar, trigonal planar, by putting another orbital right on top. So if you're looking down at the triangle and I put another one of these right on top, what's going to happen is that you're just going to bend it downward. Really important to see how they would be bended downward. So these are bending downward. So this is the planar part of the trigonal planar by this pair of electrons bending it lower. Okay, so it's really important to kind of visualize that as we try to live in a two-dimensional world. Now, where does sp3 hybridization come from, or why do we need it? Just like I've said before, it's nothing more than a theory that helps us explain dots on a piece of paper to get us to this three-dimensionality. And we always use sp3 if we count four regions of electrons around the central atom, double bonded or not. Okay, so very simply going on to CH4, and before I do that, let's consider the fact that in the sp3 family, where we're going to have this tetrahedral shape for the electron domain geometry, we have now two extra shapes that join this family because we can have lone pairs. And what I mean by that is, if we do a Lewis dot diagram, okay, I'm getting rid of these pairs here. If I do a Lewis dot diagram, there could be a scenario where I have atoms bonded to three of these four orbitals and having a lone pair. And this lone pair would push, basically, still would have electron domain geometry of a tetrahedral, but when we consider the molecular geometry, we'd be looking at the top side of a three-sided pyramid, and that's where trigonal pyramidal comes in. That's where you have basically the lone pairs pushing these three kind of downward. If you think about an umbrella, or think of a tripod, okay, and the camera on top pushing it down, and this is the legs of a tripod. So the top of a three-sided pyramid, okay, and that's where trigonal pyramidal comes from. Now you could have a scenario where you can have two lone pairs, okay, and if you have two lone pairs, then what you're going to have is a scenario we've seen before. So if we have two lone pairs, then we're going to have this bent shape for the molecular geometry. So the molecular geometry could be tetrahedral if we have four things bonded around, trigonal planar if there's three with one lone pair, and bent with 2. And so you can see how these shapes are really important to visualize, and also these shapes are only for the sp3 hybridization. However, remember the bent came in as one of the members of the sp2 hybridization. Remember when we have this scenario of what? 3 orbitals in sp3, if one of these is a lone pair, then we can have this bent shape as we just saw here. All right, let's continue on in our discussion. So we have, let's say, methane. Methane is 1s2, 2s2, 2p2. This should say 2p2. Okay, and what happens is, so we think, to have a possibility to have 4 different bonding going on, we know that carbon does bond to 4 things experimentally, but its stable electron configuration as a carbon atom is so that we only see 2 open orbitals. So some people think that, well, electron with some energy jumps away from the nucleus a little bit and jumps into a p and gives us this excited state configuration. All right, and there is where we can have 4 open orbitals. So that means that this s with 3 p's come together. So an s and 3 p's come together to give us the sp3 hybridization. Again, it's just a theory to explain. All right, and you know, it is important to understand that if we didn't have this theory, we couldn't explain the shape and the bond angles that we know. Okay, very simply, if I was to draw a carbon atom, and a carbon atom, of course, looks like this. It has a P above and below, and another P that's going to the X here, and then one P going at you and into the board. And of course, we have the S drawn, and I draw the S smaller than the P so that you can see the P's overlap. And we put the valence electrons for carbon. Well, you'd say, okay, 1, and let's just do it the way we do, 1 in the S, and then 1 each in the P's. Okay, and then our CH4 molecule we're trying to draw here, or sketch, okay, we know that the H is an S, so we have an S bonding here. Somehow we'd have an S possibly bonding here, another S bonding here, and somehow another S bonding to the S orbital. So you can see how we could have this bonding. A lot of the bonds between the P's would have to be 90 degrees. Not sure how we consider how the H bonding here. So this just doesn't make any sense for us, because experimentally, when we measure CH4, we get 109.5 degrees for the bond angles. And like I said before, if you wanted to break apart and pull these bonds apart, some of these bonds, especially the S to the 1s orbital to the 2s orbital, would be a stronger bond, because the 2s orbital has proximity or closer to the nucleus, a little more stable than the P. And what we found is that, of course, the bond energies are all the same somewhere in between an S and a P. So obviously, okay, this doesn't make any sense. So we have to consider that we've made what? 4 new orbitals, and that they would what? They would hybridize and give us a scenario like this. So this carbon would have 1 sp3 here, and then we'd have another sp3 here, and then we have another sp3 here, and of course another sp3 here. They should all be the same size. Now, I'm drawing it 2-dimensionally, so it's tough to realize, but we'll just stay in 2 dimensions for right now. Each carbon has 1 valence electron. I'm sorry, the carbon has 4 valence electrons, be 1 electron in each of the sp3 orbitals. Okay, and then we're going to bring on the what? The hydrogen, who was just 1s1. And we have a better representation or model for what we see experimentally. The bonds are all the same. The bond energies are all the same. Now this looks like it's 90 degrees as well, because I'm drawing it 2-dimensionally. So one way to help with the understanding or the dimensionality that this is, when you have 4 pairs of electrons surrounding an atom, we know it's going to be sp3 hybridization. Now, I probably should have done the Lewis dot diagrams first, so I shall do this right here. Carbon has 4 valence electrons. Hydrogen has 1. And this is the Lewis dot diagram. And people tend to, when they write these, separate these pairs of electrons like this. So it looks a lot like what I have here. But another way to write this so that you can get the three-dimensionality, this is not planar. Okay? You may think that this is a planar molecule based on how we're drawing. It's not. It's a tetrahedral. So let me try to draw for you, and this might be very helpful to remind yourself this is not planar, because you will get some things wrong thinking it might be. So what you do is start with your carbon in the middle, and we're going to put this bond, which is a pair of electrons, to the H. H doesn't have any lone pairs, so we're good. And we're going to put this bond, so these two are on the same plane with an H. Now, I'm going to make this one get thicker. And the reason why I'm making it thicker is to show that this one's more coming at us. And then I have a dotted line. And that dotted line represents one that's going back the other way. And if you blink your eyes and look at that long enough, this one's coming at me. These are in the same plane. And this one is the one that's kind of behind with a dotted line. You can visualize that these are the 3 orbitals being pushed down by this pair. And this is what we have here. And this, of course, is where we get our 109.5. This is a better way to do it. Again, we're always trying to think three-dimensional, especially when we're trying to understand the polarity. Even this is 109.5, okay? And these bonds are all the same. So again, hybridization helps us explain the fact that experimentally all these bonds are the same energy and we're getting this shape. We can't do it with just regular s and p orbitals. So let's continue on our discussion. So we have C2H6. We're going to put our carbons in the middle. We always start with the dots. The dots, using VSEPR theory, which is how the dots or electrons repel themselves into a stable shape, get us to the point with hybridization, the information we can predict, okay, and see experimentally. So let's do it. So this carbon has 4 valence electrons. Now I'll put the H's out too, and I'm just going to throw them around. As we've done before, we can always rewrite, and I'll put the H's here. And oh, by the way, going backwards on this, you can see clearly that this molecule would probably show some sort of what? If we were to write the molecule this way, this would show that this is a polar molecule. And you say, well, why, Mr. Grodsky? These bonds are essentially nonpolar. Well, if most of my electron density is on this side of the molecule, this would be the negative end of the molecule. So we know that CH4 experimentally is nonpolar. So again, it's important to know how these things are arranged. Because they arrange themselves in this shape, you can see that spatially there's no difference in all directions. Okay, all right, getting back to business here. Carbon has 1, 2, 3, 4, and then we have another one. This carbon has, well, so the hydrogen has 1, 2, 3. This hydrogen is 1, 2. And each one of these hydrogens bring 1, and then we bring the carbon in. I guess we're using red here. And there's 1 for that carbon, another for that carbon, and we're just filling in. Carbon has 4 valence electrons, so the reds are the carbon, and there is our Lewis dot diagram. If you need to, you can, which means you're going to evaluate what your carbon, and carbon is sharing 8, each hydrogen is sharing 2, and you can do the same thing if you need to. Most of you guys, I'm sure, don't have to. Okay. So you can also, again, write it, okay, this way as well. There's no lone pairs on H's, so therefore that you're fine writing it this way, okay? Okay, so now, getting back to this, how could I identify, after doing the dots, how could I identify the hybridization? Very simply is how many pairs or regions of electrons do you see surrounding the central atom? And I see 4 for each of these carbons. So therefore, Because there's 4, that means that S and 3 P's must have melded together. So that's why this is sp3 hybridization. Okay, and because it's sp3, I know the bond angles are 109.5. And because it's sp3, I know the electron domain geometry of the internal carbons, the central carbons, is a tetrahedral. That's automatic. No ifs, ands, buts about it. Okay, so the molecular geometry is also going to be a tetrahedral for both of these because there's no lone pairs. All right, polar bonds, well, between carbon and hydrogen, we say no because they share approximately equally. Polar molecule, well, the answer is going to be no as well because these electrons, even though if you think they're being shared unequally, and they're not, are being basically spread out evenly throughout, or we can say it's very symmetrical. So let's get to the orbital sketch. Okay, and let's start with our carbons. Again, we're going to live in a two-dimensional zone trying to represent 3 dimensions. Kind of hard, but each carbon is sp3, so this carbon is going to have 4 sp3s. This carbon is going to have 4 sp3s. So these are all sp3s. And then I'm going to have another carbon overlapping and giving me that, ooh, I'm just not loving life over here. It's another carbon giving me an sp3 in 4 places. So these are all sp3. Put out the valence electrons. I'll use black today. So there's 1 for this carbon, 2, 3, 4, and then 1, 2, 3, and 4. And then we're going to put in the H's. And of course, they're just S's. And it's pretty simple now, I'm sure. Notice, party people, we do not have a double bond involved here. And the reason is we've used all the P's. To have a double bond or a triple bond, you need unhybridized P's. Well, we've hybridized all of them. sp3 means what? We've used all of the P's. So there's no unhybridized P's, so there is no double bonding in sp3 hybridization, something to be aware of. Now this looks like it's a planar molecule. It really is not. As I've done before, okay, I'm going to have what? I'm going to have, let's say, this one and this one in the same plane, this one coming at you, and this one coming behind. And this would be an H, H, H. This would be a carbon coming down, okay, and it has what? 1 coming from behind it, 1 coming at you, kinda, and then 1 on the same plane. And so it's not going to look exactly how you think it will. So hard to do that, but again, that's more representational of what you're going to see. And when you have a long chain hydrocarbon, I know in organic chemistry you might be writing like the C's this way, but in truth, in books you'll see them going up and down. And the up and down motion of the carbon backbone is because we're dealing with this tetrahedral. Don't forget there's 2 H's here. Okay, for every carbon there's 2 H's. Okay, so that gives you that tetrahedral feel. Again, have to think 3 dimensions. Okay, now we didn't answer some of these. So there's no polarity here, so there's no overall dipole moment. Let's go on to this one. All right, CCl2F2. I like this one. So let's do the dots first. Put the dots in the paper. I want to use carbon. I know carbon has 4 bonds it can make. And I'm going to put chlorine here. Let's just do this. Let's be fancy and see if I can get you on this. Let's put the Cl here, an F here, and an F here. Okay, let's put in the valence electrons for carbon. 1, 2, 3, and 4. And let's put, for chlorine, of course, halogen is going to have 7. So I have to show all 7. Can't be lazy here. Can't leave any lone pairs. Hydrogen doesn't have any, so we didn't need any. Can't do these without the lone pairs. So this is how you would do the correct Lewis dot diagram. And this is an example of a freon molecule, a molecule they would use, okay, in refrigerants that is really bad for the environment. So in any case, this is my Lewis dot diagram. All right. Now, I didn't draw the dots according how they attracted. The fluorine is going to be much more attracted to the electrons than the chlorine. So these actually electrons will be pulled toward these halogens. But in any case, you get the feeling. Now, of course, the first thing we say to ourselves is, what kind of hybridization do you have? I know we're in a sp3 worksheet, but you count how many, what? 1, 2, 3, 4 different regions, okay, gives us sp3. Because of that, the bonds, or how the electrons repel, will be in a 109.5 degree. Because of that, the electron domain geometry must be a tetrahedral. Okay, very important that those go synonymously together. Now, the molecular geometry winds up being tetrahedral because everything's bonded. There's 4 places, okay? Now, polar bonds, absolutely yes. There's 2 different nonmetals with very different electronegativities or attraction for electrons. Polar molecule, that's where people are going to get confused here. Now, why? Well, what people do is they may say, well, Mr. Grodsky, I learned that if it's symmetrical, then the element, or the molecule, I should say, is going to be nonpolar. So you would look at this and say, well, this is very symmetrical, 2 Cl's, 2 F's. And this would be symmetrical if the molecule was planar, but it is not. So this is going to be a polar molecule because it is definitely asymmetrical. If you look at it planar like this, you would say, oh my gosh, I don't agree with that. But this is not planar. Let me help you. Let's go to the 3-dimensional drawings here. Here's carbon. Let's put chlorine and the fluorine on the same plane. Let's have chlorine come at you, stick out. Okay, that's what this means. And then have fluorine come behind. So what does that mean? That means I have these pair of electrons pushing down these. This is the top of the what? The pyramid. The top of the what? The tripod I talked about. Right. So how this is not at all symmetrical. Think about a tripod. You got the chlorine on the tripod, and then you got the 3 legs pointing downward. Show me the symmetry. There isn't. And if you were to draw the dipole moments, which we have to, we always go from the positive to the negative. All of these elements are more electronegative than carbon. They're closer up and to the right. So they're more electronegative. So they're all going to be the negative part of the bond. So when I draw them, and I'll draw them over here, it's going to be the positives going to the negatives. Now, chlorine, and again, it's not going to be perfect, but fluorine is what? More electronegative. So these arrows for the fluorine would be bigger because they're much more electronegative. And nothing's canceling out here. Okay, nothing is canceling out. Now we have a weaker arrow pulling up, and we have 2 bigger arrows pushing down. So the overall dipole moment, hard to see this, would actually be somehow pushing down this way. Okay, so the overall dipole moment is pointing downward. Now, keeping it flat, hard to, this would look like they cancel out, but there is an overall dipole moment, okay, given how I drew it this way. Now, if you're trying to draw dipole moments, keeping it planar, as long as you draw one, that would work. But you can see how this is more advantageous to draw it this way and see it this way, okay? You have to see 3 dimensions. So let's go to our, and again, I think we can skip the orbital sketch here because it looks like this, except now you're going to have what? Fluorines and chlorines on the end. And I'm not going to skip it. I'll just do it quickly. Okay, so let's go there. Don't want to shortchange you, especially if you're doing this, okay, very fast speed. Okay, so the central carbon has what? 4 sp3 orbitals. It has 1, 2, 3, and 4. Okay, let's get rid of some stuff to get out of my way, although this is really important to see. Okay, now who's going to bond? Well, let's put fluorine here, and fluorine is unhybridized. Why? It's terminal. Okay, so I have to draw all the P's, all the flower P's, and then the S, and then I have to put in the valence electrons. And you should be able to do this at this point, party people. Here's 1, 2, 3, 4, 5, 6, 7. Notice I don't fill this one. And we do it over here for chlorine, which is going to be exactly the same shape, right? Because it has 7 valence electrons. Now, in truth, these orbitals should be what? Bigger, okay? You must say why, because it's an n equals what? 3 element, but it's okay. So 1, 2, 3, 4, 5, 6, and 7. I forgot to mention these are all sigma bonds, right? All sigma bonds that directly overlap are not going to have any pi bonds. Okay, and then we'll do in the other one. This is getting to be fun. And this is fluorine. And I'll draw my S here. And same idea. 1, 2, 3, 4, 5, 6, and 7. Don't fill that one. And we need one more. And this one would come right here. Whoop. Trying to make that all fit. And boy, I'm getting sloppy now, but hey, I'm tall. All right, so 1, 2, 3, 4, 5, 6, 7. All right, so moving on in, that of course is a polar molecule. Okay, NH3, more simpler ones coming up. So let's do it. Oh, and of course, all the bonds were sigma, right? All these were sigma. Sigma, direct overlap. All right. So NH3, let's go to the dots. N, 1, 2, 3, 4, 5. I have a practice of putting 2 dots on top of N. N is famous for being a base, for having a lone pair there. H brings 1 to the table. And this is my 2-dimensional Lewis dot diagram. Looks pretty planar, but it's not. Why? The first thing I see is that there are 1, 2, 3, 4 regions of electrons. So that tells me the hybridization has 4 different orbitals, an s and 3 p's. The bond angles are 109.5. Electron domain geometry, of course, is a tetrahedral. And the molecular geometry is not tetrahedral because we have to consider where the molecules or atoms are. So if we were to draw this with a better representational shape here, here's my N. My lone pairs are going to be on the tripod. I'm going to have one leg of the tripod bonded to my H. One of my H's coming at you and one coming from behind you. Okay, you can see clearly that the shape is the top of a 3-sided pyramid. And we call this a trigonal, like a triangle, trigonal pyramidal. So it's a triangle, it's a 3-sided triangle, trigonal pyramidal. And that makes sense if you think it that way. Now, the bond angles are 109.5, but you should be aware this lone pair, as we said before in the other worksheet, because it's not bonded to another atom that attracts this pair actually comes closer to the nucleus and repels these downward a little bit. So what happens is this bond angle becomes something around 104. Now you don't have to know that. 109.5 works fine, but it will repel something a little lower. Okay, be aware lone pairs do that. Okay, let's draw the orbital sketch. Okay, and of course we're going to start with sp3 orbitals because we counted 4 pairs. All right. And these are all sp3. It's really good to draw them where you can. All right, and we have 1, 2, 3, 4, 5, and of course we have our H with the S, and that's it. I really think we're getting to a point where this helps us more than the orbital diagram at this point. But what do we have here? Polar bonds? The answer is yes, we have polar bonds. Nitrogen and hydrogen do have a great difference in electronegativity, so they're being shared closer to N. N is a little more stronger. N is actually the third most electronegative atom. So it's going to pull this pair closer. So they're sharing electrons unequally. So what does that mean, party people? Well, that means if I get rid of these blue arrows here, that we're going to have an overall dipole moment. So let's draw that. Let me just draw the dipole moments here. Let's do that in a different color. Who knows? I'll just stay in blue. So we're going to have dipole moments. So we're going to have the positive end of the molecule pointing in, positive ends pointing in, positive pointing in. There's no dipole moment here because it's just a lone pair. So what we have is essentially the three legs of the what? Three legs of the tetrahedral here, or the tripod, gives us an overall dipole moment that actually would point upward toward the end. So all three of these do not cancel, and that would give us a resultant vector. Vector has what? Quantity, the size of the arrow, and direction. So if you were to draw this, and again, I got a lot of stuff going on here, but hey, who doesn't? So if I go back to my Lewis dot diagram, oops, ooh, hello. This, I would draw an overall dipole moment going this way. I'd have to understand that I'm visualizing this. Okay, polar molecule, yes. Why? Well, if you think about the entire molecule, there is an N on top where the H's are being pushed downward. The electron density, including the lone pair, is in this region. So this is the negative end, and where the H is, it's the positive end. And as we've learned before, we can actually have hydrogen bonding here. These H's having their electrons pairs are being pulled away so much that you're just leaving what's left as a proton at the end. It's electron deficient H. So all of these H's, okay, their electrons are being pulled closer to the top part. So these are the positive ends. They're so positive, they're basically protons dangling out there. And you can do something called hydrogen bonding. That's the strongest type of intermolecular attraction. Any case, so yes, it's a polar molecule. Is it asymmetrical? Yes, but I rather you think in terms of the three dimensions, that you have a lot of electron density on one area and you do not on the other. Okay, and that's because you understand the three-dimensionality of this shape. Okay, so we've got one left. Okay, and now we're going to do with water. Okay, very simple, probably done it 100 times. So we have our oxygen in the middle. It has 6 valence electrons. In fact, I'm going to draw it like a lot of people do first that confuse themselves. Okay, so let's do oxygen. And this wouldn't be wrong the way that I'm doing business here, but it may confuse you. So oxygen has 6. Hydrogen has what? 1. So we bring 1 in, and I put the dots on the table, which we start with the dots. And then, of course, we count regions of space of electrons. We can see that there's 1. Even the lone pairs we count, 2, 3, and 4. So party people, we've just discovered that there's 4 regions of space, so the hybridization is sp3. The bond angles are 109.5. Electron domain geometry is tetrahedral. And the molecular geometry, whoa, it's not a tetrahedral. There isn't 4 atoms. The molecular geometry is where the atoms are. Now, you might convince yourself that this is linear the way that you drew this. But you have to think about the three-dimensionality. This is not linear by any stretch of the imaginations, because if water was linear, okay, if water was linear, we wouldn't be here to talk about it. Okay, one of the reasons for life is that, water is polar because it's a great solvent. So my friends, this although that I could accept it, this is not representational. You may say, okay, polar bonds, two different nonmetals sharing electrons unequally. Okay, oxygen is more electronegative than the hydrogen, so you pulled closer. And you may say because it's linear, it's the same on both sides. But think about what the shape would be. Let's make a lone pair the top of the tripod. Let's make the what? The H one of the legs. And let's make, okay, the other H coming at you, and then the other what? Leg is a lone pair. Can you see the shape now? Yeah, I bet you can. Okay, it's a bent shape. This is bent. And this is the last family member. So this would be bent. You have to consider for molecular geometry where the atoms are. The ones we've done before him, they were all filled. If you look very carefully, okay, Cl2F2, the Freon molecule, these were all filled. So was tetrahedral. So were these guys. Okay, so one lone pair in the family is the top of a three-sided pyramid. Two lone pairs is a bent shape. Okay, and again, you may fool yourself, just like you may fool yourself to thinking that this, okay, is symmetrical. You may fool yourself to thinking that this is symmetrical. And that's why saying symmetrical and going fast with a mnemonic isn't the best dressed situation. You have to understand the three-dimensionality. Okay, so how would this come out to be? Well, if your eyes, here's an eyeball, looked straight down these two lone pairs, and I know it's hard to imagine that, you can see that way. If you look straight down these two lone pairs, okay, drawn better probably, you can give me that. So anyway, real quickly, the sketch would be an sp3. So I got 4 orbitals, sp3. So oxygen is sp3 hybridized. It has 6. We'll do 1, 2, 3, 4, and then of course the we got our 6 valence. Okay, and then of course we have hydrogen with its 1. Now again, this orbital sketch makes you think that, is this 90? No. Again, it's basically hard to draw them. This is really helpful to think of it that way. All right, so I hope that enlightened you, even if you've seen this stuff last year, to think three-dimensionality is really helpful to draw these structures at this point in time. All right, so hope that helped.